So now I will hand over to the next theme, that is the quantity and quality, two sides of the same climate change coin. And for this theme, the moderator is Professor Vikrant Jain, who is the discipline coordinator and of Earth Science discipline. And just I will introduce him, and then he will take over the session. And so he is, he got the prestigious National Geoscience Award in 2018. Of course, he is also representing the head of all the discipline of the science. And you yourself, you'll know that the interest, though he works on river geomorphology, but because I knew that to handle stalwarts like Professor Raghu or Goyal or Professor Mishra, he is the right person to moderate. So thank you very much, Professor Jain, to have accepted this responsibility. Please, the session is yours. Unmute, sir. Unmute.
Many thanks, Professor Manish, and I welcome all on this panel on the quantity and quality, which is the two sides of same climate change coin. And in this panel, our panel members are Professor Vimal Mishra, Professor Raghu Murthukote, and Professor Manish Goyal. First, we would like to listen to their thoughts, and then I will open it for the discussion. So first, I invite Professor Vimal Mishra from IIT Gandhinagar. Professor Vimal Mishra currently works as an associate professor in the discipline of civil engineering and earth sciences at IIT Gandhinagar. His current research interests are hydrological modeling, remote sensing, climate change, drought, floods, and heat waves methods and techniques, modeling statistical analysis, data analysis. He is currently working on drought and water availability in India under current and future climate. He is a recipient of several accolades such as WARI fellowships, Max Planck fellowships, and DAAD fellowships. I invite Professor Vimal to discuss this part.
Yeah, so thank you, Professor Vikrant Jain, and good evening, everybody. Good evening, Raghu and Manish. I hope things are well at your end.
Good evening.
So, I mean, it's a pleasure to be here and discussing about the climate change and the challenges related to water security, water quantity, water quality, right? So when I was thinking about what to put on my slides, because this topic is so broad and, I often feel difficult to sort of summarize in a few slides or what basically should be discussed, what not to be discussed. So my slides are not very well prepared. I put the material selecting from here and there, and I will have this presentation basically in the discussion mode, and I'll discuss that what we have been doing. And I think Professor Raghu Murthukote is here, Manish is here, and they will provide more detailed, probably the challenges and issues that our country is facing regarding water security and climate change. So let me do the full screen. And so I'll be talking about water security challenges in India under warming climate. And this is the topic which probably everybody is well aware that climate is changing, climate is warming, and India has been historically facing basically the challenges related to water availability and so on and so forth. So I'll start from this slide. Basically, what are the grand challenges for future food and water security in India? Because when we talk about water security, there is food security is very well related, because in India, most of the water consumption happens in agriculture. So if we have problems related to water availability, the first sector that will respond to this challenge will be, of course, agriculture, and then food security also becomes a big problem because our population is increasing. And so these two things are very well correlated and they go side by side. So what are the impacts of warming climate on water availability and demands? So availability, basically we can know a little bit in a better sense, but water demands remains a key challenge, that how water demands will change in response to climate change in the future. And there are bunch of issues related to that because we don't have sort of observational data sets that we may like to have in terms of credibly understand or that how the water demands are going to change in response to climate change in India. But one thing is which we may expect that in under the warming climate, irrigation demands may go up because farmers may like to reduce the negative impact of climate change on their crop yields. So they may end up irrigating more often to cool down the crops, or the irrigation water demands may increase. Similarly, water demands in other areas also increase. And there are projections basically suggest that agriculture may face significant increase in water demands in the coming decades and years. So the second challenge, or you can say that observation that we see based on the past record or observational record, that our rainfall characteristics in the country has been changing, and that has implications for groundwater recharge, that also have implications for agriculture and other things, but that has a very direct linkage with the groundwater recharge. So what I mean to say here is that the rainfall characteristics means the low intensity rainfall or the number of rainy days have been significantly declined. And there are regions or aquifers that where the low intensity rainfall is extremely important for groundwater recharge. So we may argue that whether these changes are happening in with response of climate change, or there is other large scale climate variability related factors that are causing these changes. But certainly the groundwater recharge is less, we are pumping more, so that puts a extreme challenge for water availability. And that also related to rapid groundwater depletion, and irrigation frequency is expected to rise. Surface water availability under climate change will be hit because of the increased evaporation. We may not have very large storage for during the entire dry season, right? And then crop yields are also declining under warming climate. So these are the challenges. I mean, um, but there might be multiple other challenges related to how we respond to these challenges, what are the socioeconomic angle related to these problems or challenges. So I have few slides where I'll discuss like what we have been doing. And so our Manish, what is the time limit? Please tell me now so that I can basically, because your session is running late and I may go like half an hour, which I really don't want to do because. So this is the summary slide. If you understand this, then I really don't need to talk too much about what I have. So very quickly, there has been a significant warming. We all know, right? We don't need to sort of go into deep. You can see like post-monsoon season, which is major crop growing season in India from October to, October, not to December, but October to December. That you can see that tremendous warming has already occurred, more than 1.2 degrees Celsius. And then there is a warming in other seasons also predominant, except the region that is heavily irrigated. You see pre-monsoon and winter season, there is a cooling, and that is primarily because of irrigation. And people also say that that is because of aerosols, high aerosol loading in that Indo-Gangetic plain. Right. So there is no doubt we are facing extreme or significant warming. A number of So precipitation characteristics have changed. So there has been a decline in the monsoon season rainfall. There has been a significant decline in the number of days with low intensity rainfall. On the other hand, there has been increase on the number of days with high intensity rainfall. But that is not as predominant or as prominent as we see the decline in low intensity rainfall. And these changes have been observed, and they have the implications when we talk about the water availability and water security. And that is very well related to groundwater recharge. So what we found, like low intensity rainfall is critical for groundwater recharge, at least in the North India or North Central India and Northwestern India. South India, the aquifer characteristics are significantly different than the Northern India. So there you may say like high intensity rainfall is more favorable. So once the observation changes that we have been seeing are not very supportive in terms of for the groundwater recharge, at least in the North India, and that is a big challenge. Groundwater has declined in the North India. I mean, we all know that there have been a lot of studies, lot of work, both observational bells and GRACE. So tells us that there has been significant decline. And if we put on top of this decline, which is primarily due to pumping for irrigation, and put like the changes in rainfall characteristics. So uh, we are facing less recharge, more abstraction. So that is not sustainable for water availability and also for crop production or agriculture in India. This is, I will not go into details. So the droughts also keep occurring, right? So in the last few years, the monsoon season rainfall or the summer monsoon has been a little bit, I mean, we have faced more number of droughts if you look last 2 decades or so than the previous 2 decades. And this 2014-2015 drought in the Indo-Gangetic Plain was a very rare event, once in 500 kind of a event. And what is the implication of that? That it not only affected the surface water resources, but the groundwater in the Indo-Gangetic Plain during the during the dry season, December to March, was substantially declined. And that tells us that whenever we face drought, we also end up pumping more groundwater for survival. And if the groundwater is already depleted or not in a good shape, and under the climate change, if we see consecutive droughts, then that may pose quite serious challenges that how on the water availability, right? So droughts and rise in temperature is related to food grain production or crop yields. So I mean, we all know that drought affects crop yields. So far, like warmer temperature also results in the decline in crop yield. So that's one thing we want to highlight here. The other thing is that whenever these drought and extreme warm temperature occur, which are more likely in the future climate, they have much larger implications for food security and also for groundwater pumping and also for groundwater depletion. So these all factors are interlinked, and we have to understand when we talk about how climate change will affect the water availability. It is, and it can affect in very many different ways. So in future, what we are going to see or witness, I mean, there are projections that suggest that summer monsoon precipitation over India is going to increase, and that we also see like there is a 6 to 9% increase depending on the models. You select some models so larger increases, some models so slightly lesser increases. But we need to understand that this will happen during the monsoon season, and then in dry season, your atmospheric water demands or irrigation water demands will increase in in I mean, there may be a larger increases during the dry season for water demands, and not necessarily this increase in rainfall you can use for the dry season to meet those demands, and that can create challenges for water availability, especially during the dry season. So many times people say that there is going to be more rain, but that not necessarily means that more rain means we are not going to face water related challenges in the future, because we have to understand that more rain in what form is just an extreme rainfall, or it is uniformly distributed throughout the season, and how we are going to store that water in the surface water or groundwater reservoirs. So that is a key question we need to understand. So what I mean, we have been doing very
Vimal, I request
recently,
to
this is
summarize
unpublished
them.
work. So we have been looking at that. What is the likelihood in India to get two consecutive droughts? And two consecutive drought means monsoon failing two consecutive years, because under climate change that can put a huge risk in terms of water availability, food production, and other things. So here I'm showing like we use data from MADA, which is Monsoon Asia Drought Atlas, starting from 1200 to 2018. And we identified that how many times it has happened in the history of last 800 or so years. So we found only 6 times we have experienced two consecutive droughts during the monsoon season. And then we have looked at very large ensemble of last millennium from the CESM, and again we try to sort of understand that starting from 850 to 2000, that how many times we get two consecutive year droughts. And you can see like the probability or risks of getting 2002 kind of a drought is very, very low. So it's like 0.73 per 100 years. So it's less than 1% getting two consecutive droughts. And those droughts are very well linked with ENSO or El Nino Southern Oscillation.
So Vimal, will you
Whether
please
two
now summarize
consecutive
them?
droughts will occur in future, answer is yes. We cannot avoid, or we cannot say that it will not happen in future under climate change. When we are saying that monsoon season precipitation is projected to rise, that doesn't mean that India will not or may not experience droughts in future. Droughts are part of climate variability. They have been occurring, they will occur in future. But we can say that the failure of monsoon two consecutive year, in a sense that it can create a countrywide drought, is really low, and it is going to decline in the future. So we have just once one event in let's say 300 years in the projected climate, when we can witness the two consecutive countrywide droughts that can create food security or water security challenges. I mean, so these are this is what I have for today. So in summary, I can say that this is the topic we have to sort of study from the multiple angles, not just based on how climate change will affect the net water availability in sense of rainfall or in sense of our reservoir or groundwater storage, but how people will react to climate change, how the adaptation will happen, what new technology will come in terms of intervention, and what would be the overall. But having said that, the net or the key message we can take is that the risk of water scarcity or water unavailability or in the under the climate change is not going to go away, despite there are projections suggesting that there is an increase or in the summer monsoon rainfall in India by most of the CMA 5 or CMA 6 models. So Manish, that's what I have. I would be happy to have if there are any questions. Thank you very much.
Many thanks, Professor Vimal. And now we will move to our next talk. Next talk will be from Professor Raghu, who is faculty in University of Maryland. Professor Raghu is an Earth system scientist studying the studying the interaction between physical world and the lives, and explore the co-evolution of life and climate what it means for sustainability. That's a very wide areas. And his research interest lies in data analysis, regional Earth system modeling, and predictions, which are combined to advanced process and predictive understanding of Earth systems, especially at the regional scale. His further research areas include producing region-specific predictive information at daily to seasonal time scale that is useful and usable, and what is scenario for the annual scale, and process understanding on the role of oceans in tropical climate variability at diurnal to decadal time scales and extreme. So I welcome again, and I invite Professor Raghu to discuss this part.
Thank you, Manish and others. Can you hear me?
Yes, we can hear you.
Okay, so since this is a panel discussion, I'm not going to go into a seminar mode. Just want to point out, this is for this year's monsoon, and this is the rainfall. There were a couple of cyclones and depressions that affected the distribution a lot, and there is a normal, and that is the difference. So you can see the impact. But what strikes me when you think about the water quantity.
I think you need to share the slides.
No. Yeah, no.
Okay. I said share screen, but are you sharing or am I sharing?
Yeah. We already
now
said.
we can see.
Okay. So are you controlling it?
Yes.
Yes. Okay. So can you go to the next slide? So what strikes me when you think about the 5 C's you're talking about and the water quality, quantity, and access that was mentioned before are things like this. Each year the monsoon looks different. These are trends in annual rainfall, so it's a bit smoothed out, and a lot of regions are not significant. But you can see that the distribution tends to be very erratic, and the prediction skills at local scales is very difficult. And the question of dynamics as to what determines such local scales, if you think of India as a popcorn kettle and convection as popcorns popping everywhere, then what is really controlling the large scale dynamics, and what is controlling moisture supply, and how the Indian Ocean warming is affecting the moisture supply and the distribution and so on, are really challenging. If you go to the next slide, I think the warming of the Indian Ocean is also very unique, because the significant amount of heat is actually coming in from the Pacific Ocean through the Indonesian seas, and the Indian Ocean warming actually now seems to control the Atlantic meridional overturning as well as the Pacific response to the anthropogenic forcing. So Indian Ocean is acting like a clearinghouse for the ocean warming, especially because the Southern Ocean warms very fast because of its unique channel configuration, and that's also pumping heat into the Indian Ocean. And you can see this ocean heat content anomaly over the top 2,000 meters is also quite significant over the Indian Ocean. So no matter what happens on land, we are not going to have much control on what happens over the ocean. And if they decide to pump in a lot of moisture for every instability, then we're going to have massive extreme events and widespread extreme events and so on. Next slide. Everything about the monsoon is changing. The onset seems to be occurring later since the mid-1970s. And that was considered a regime shift in climate, which is seen everywhere. But there was also a return shift in the late 1990s, which doesn't seem to have returned the monsoon. And at the same time, it seems like withdrawal was happening earlier, so squeezing the monsoon season, and the rainfall decrease is about 10% over the last 50, 60 years. But the rainfall distribution and intensity within that is still occurring on active break periods. So active periods are very extreme now, and the dry break periods are becoming more frequent and extended and so on. While the signal coming in from the ocean in terms of the northward propagating features, the mesos, monsoon, intraseasonal oscillations have slowed down, which is consistent with the general cyclone slowdown across the globe. So that is affecting the rainfall as well, because the synoptic depressions coming in from the Bay of Bengal are increasing, but the low frequencies at 10 to 20 days and 30 to 60 days are decreasing. So if you go to the next slide, there is lots of bad news in terms of continued model biases, especially we know that the CIMIC 5 models didn't do the historic trends very well, and there is dynamic inconsistency there. And that dynamic inconsistency continues into the projections as well, in terms of the ocean warming, land warming, and so on. So I'm very nervous about projections about the monsoon, especially because East African monsoon is also shown to be wrong, which is related to the Indian monsoon through the ITCZ. So the basic rainfall distribution and the extremes and the non-linearities you get in terms of the runoff associated with the extremes, the loadings and the water quality issues and the health issues, I think are very serious. So the forecasting and at S2S timescale then becomes critical. Fortunately, India has invested a lot of money, and examples from 2020 and 2019 show that there have been many examples of very successful forecasts at short and medium range, and maybe even at extended range. If you go to my next slide, essentially, I think non-local factors are going to complicate all 5 C's of water problems over India. We have to be really careful. And improving predictions and projections is a good idea, but S2S timescale, which has become a focus as the multi-year timescale, societally relevant timescale, and so on, I think it will become critical, because this so-called ready, set, go framework, where you use seasonal forecasts to ready the whole water resource management, agriculture, and other water resource problems. And set is where extended range comes in 2 to 4 weeks, and go is the weather time scale, like 1 to 3 days and 3 to 10 days. So this framework needs to be developed, and then the last mile problems of actually using the forecast, whether it is to deal with the droughts or the floods, is going to be very critical, I think. So that's my short presentation for the panel. Thank you.
Many thanks, Professor Rakhu. And so we will keep the question and the discussion at the later phase. And before that, I would like to invite Professor Manish Goyal from IIT Indore. Professor Manish Goyal is currently designated as an associate professor at IIT Indore. His research interests include resilience of river basins and hydrological modeling, hydroclimatology and statistical nanoscaling, irrigation management and crop modeling applications, and multivariate statistical analysis. Machine learning models and data mining is also one of his research interests. He has several awards and accolades for his names, including ranking a top 2% scientist in the list prepared by Stanford University, and among the top 500 of the world's more than 42,000 researchers in the sub-area, environmental engineering, and the sub-team of meteorology and atmospheric sciences. He has received the Best Theoretical Oriented Paper Award in American Society of Civil Engineers in 2018, and being awarded American Society of Civil Engineers Visiting International Fellowship in 2019. I invite Professor Manish to discuss his viewpoint.
Good evening, Professor Vikrant. Can you hear me and can you see my slide?
Yes, we can hear you, and we can also see your slide.
Yeah. Okay, I'll make it full slide.
Yes.
Okay. So thank you, Professor Manish Kumar, for inviting me in this virtual conference on 5 Cs. So I think Professor Raghu and Vimal has spoken many things. I will add few more things in addition to whatever has been spoken earlier. Before that, I think you included COVID-19 in this virtual conference. So I thought it will be a great pleasure for us that we have just published a book on COVID-19 by Springer. It's an integrated risk of pandemic, COVID-19, impact, resilience, and recommendations. So this was, I think authors are from around 12 countries across the world, so US, Canada, Europe, Australia, Japan, and this got like 450 pages. Though this includes the recommendations, impact on various industries, MSME, agriculture, water, forest, how our economy is impacting. So we try to give the different perspectives of COVID-19 in last 6 months, basically from March to September, because October we published the book. So that I thought I would bring this to your notice. And let me discuss something that was not discussed, like resilience, ecosystem resilience of Indian river basins. Resilience is something that was given by Hollings in somewhere around 1970s, 73. It's like an ability to sustain or a capacity to withstand against the disturbances that a particular system hits, either by drought, by flood, or any other disturbances, forest fire, volcanoes, impact. So in this study, what we have done, we try to couple the water cycle and the carbon cycle. Generally, the hydrologists or climatologists, they talk only the water cycle. They leave the carbon cycle aside. So here the crux of the problem is that we try to couple both the water cycle and the carbon cycle. And from that, we have come to the analyze like how these ecosystem resilience is varying across the India at different river scales. So for this purpose, we use the MODIS net primary productivity data, evapotranspiration data, and ecosystem resilience definition is very simple, like how my ecosystem will behave under the drought condition, whether my ability of the system is remain low, same, or even high productive under the water limiting conditions. If my abilities goes up under the water limiting condition, I will say that my ecosystem of that river basin is resilient. Otherwise, we will say it's non-resilient. So basically the two parameters, net primary productivity, that comes from water cycle, evapotranspiration, that comes from water cycle, and that NPP comes from carbon cycle, they play the major role. And ecosystem resilience is basically the NPP divided by evapotranspiration. And that's how we have done it. This was done on spatial resolution of 1 kilometer by 1 kilometers. And from that, we got this this map in which we computed RD, this index of resilience. That's how the water use efficiency will vary in terms of dry and in terms of mean systems. So if you see it here in this 22 river basins across the India, as per CWC classification, Central Water Commission classifications, we found that only 6 out of 22 are resilient. Rest of them are not resilient. If I talk about few, like Indus River Basin, Brahmaputra River Basins, and Penna River Basin, these 3 plus 3, 6 river basins are only resilient. Rest of them are non-resilient. And India being one of the largest populous country where most of my population lies in Ganges basins and central India, these are part of non-resilient. So here, as a hydrologist, as a climatologist, as a practitioner, we need to focus how we can help to make our ecosystem resilient at river basin scale. Another stuff that we have carried out on same, we divided in India as a geopolitical boundaries in terms of districts or in terms of states. How the things are happening across the each districts or across the each states. So out of, let's say, 634 districts, we found out like 241 or 38% districts are only resilient to this phenomena that we have considered as drought in terms of hydraulic resilient. And here are the area how the resilient systems is there, whether they are totally resilient, slightly non-resilient, moderately non-resilient, or severely non-resilient. Because as a scientist, we need to understand how our ecosystems of different regions of the country, they are responding to hydroclimatic disturbances that we have considered droughts. Because we need to feed the 1.3 billion population, and food security is very important. And out of the food security, that NPP, the vegetation comes, even carbon sequestration phenomena happens. They are pretty much important to feed under the increasing the intense frequency, severity of the drought events under the future, like CMIP5 and CMIP6. They say that there's an intensity, change in the intensity, severity, and frequency. They are going up and up. So this is the one of the stuffs that I would like to bring the notice. Another second one, or probably this is the last one, that I would like to bring the notice, the Himalayan glaciers or Himalayan region, Indian Himalayan region, or third pole water, where the around 65% of India population total, North India and Northeast India is dependent on, how the things are happening at Indian glaciers or Indian Himalayas. So in this study, what we have done, basically, we try to find out how the glacier lakes, those are there at Himalayan, whether they are posing any threats, how their changes is happening in different states, Jammu Kashmir, Himachal Pradesh, Uttarakhand, Sikkim, Arunachal Pradesh, whether they have been increasing with respect to the time, decreasing with respect to times, how many number of lakes are there which are hazardous, they have high impactful on the downstreams or urbanization, or how much is the risk. Like if you remember the events of 14th of June or 13th of June 2013, Kedarnath flood, Glof that happens, that was very severe. So such kind of phenomena, if they happen under these climate change scenarios, so how they're going to happen? So here are the few things like lake size distribution of these lakes, that totally we found around 329 lakes of more than 0.05 square kilometers. So out of that 129, or approximately 39% of the lake, they were smaller than the 0.1 square kilometers. And 178 lakes, they are ranging between 0.1 to 0.5 square kilometers. And there are 22 lakes which have 0.5 square kilometers area here. So these are the pretty much concerns for all of us. And in 1993, area was covered approximately 56.8 square kilometer. In 2018, so in a span of 26 years or 27 years, it has gone up by 65.80 square kilometers. So things are changing at Himalayan glacier, and we need to understand. So these are all remote sensing data applications that we have carried out. How they are bearing on each of these states, Jammu Kashmir, Ladakh and Jammu Kashmir, obviously now, Himachal Pradesh, Uttarakhand, Sikkim, and Arunachal Pradesh. Here we gave some kind of classification. How many glacial lakes, they are very high risk, moderate risk. Out of that, we found that Sikkim has the 17 very high risk lake. And Gangtok being at the downstream, one of the highly urban accumulation. So that we need to take in consideration. Jammu Kashmir has only 4 very high lakes. So I think this is all 2 points from my side. I hope I am on the time. So thank you very much.
Many thanks, Professor Manish. And yes, you are very much within the time, and it was again an interesting talk. So we now have a number of interesting talks ranging on the climate change and its impact on water security, especially on drought conditions, and also on the ocean-land interaction, and there's future challenges in the forecasting and the projections, and also the ecosystem resilience, which is going to be a major challenge. So future is going to be tough. I mean, it looks very scary. So I will initiate a discussion on these topics. So I invite all the members. So please go ahead and then raise your questions. Please unmute your mic and then just start discussion.
I think I can start, and then others may join me. I think what Professor Raghu Murdugutte presented, that makes a lot of sense. And because when it comes about the adaptation against the climate change, we need seasonal to sub-seasonal scale forecast. And as it was also mentioned that India is making huge effort to improve the entire monsoon forecast, and also the weather forecast ranging from 1 to few days. So if you look, I mean, today's this Prime Minister Modi inaugurated the largest solar park, which is so-called going to be the largest solar park in the world. And that is a grand step in direction of climate change mitigation. So similarly, I think when we think about water security or water quality challenges and how that can affect different sectors, we need these kind of big leaps in direction of adaptation. And this short to sub-seasonal forecast can be one thing, but of course there remains a lot of challenges. But because if you talk to farmers, or if you go to municipality people who manage the urban drainage system, they will still say that they they are not being able to use this forecast which is being generated in a best possible way for the decision making. So there is not just a challenge of we make progress in one direction, but we need to put various elements together on the same page in order to sort of meet this grand challenge that however water availability, water security will affect different dimensions of the socioeconomic fabric. And then we have the unprecedented events like COVID-19, which disrupt everything all of a sudden, right? So in future, I'm not saying the pandemics like will occur will more frequently. No one knows what will happen, but we may have once in many year event. They may disrupt entire our ability to make the right decision at the right time. So these are some initial thoughts, but I think the climate change adaptation has lot of scope, and we need to do lot of things in that direction.
Yes, in fact, adaptation is going to be the major key. This and and it has to be done at the farmers and at the social science level. I mean, how our societies are going to adapt and what kind of variability will be there from basin scale to basin scale, or from state to state, or maybe within a state, from district to district. So India is very diverse culturally, and also if you look for the river basin wise, the diversity is there. Rivers are different, the hydrological scenarios are different, and then how the different societies will cope, that will be the challenge. So the things are not going to be defined in a coherent way, and I think it has to be dealt in at the small scale processes, and then decide how the different places this adaptation will work.
I think I'm glad. Can I say something?
Yes, please.
Yeah, I am glad that you mentioned social science, because the problem with projections is that in the near term, which is a useful time scale for decision horizons, model uncertainty dominates. Once you go beyond 20 years, the scenario uncertainties dominate. So you can change scenarios and produce lots of different results. So for a country like India, social science is more than critical, because we don't even know the mental model that people use. But the problem is to build on what is successful. Cyclone management has become very good. Mortality has dropped really a lot. And even as the cyclones are rapidly intensifying and hitting the East Coast and the West Coast, because the West Coast is a new thing, it may be a decadal variability, but nonetheless, the way the forecasts are taken seriously and action is taken at all levels is very good. And then the additional good news is that states are trying to make their own decisions, like Kerala, I think, and Bihar decided IMD was not responsive enough, so they said they may go to SkyMet. So the idea of private players coming in and producing useful information, people call it usable or use inspired and so on and so forth. But the social science aspect is so critical, and yet we have these meetings often without social science, and we present the same results of looking at CIMIC 5 models and saying this and that. So resilience and vulnerability go in the right direction, but they are still done from a very physical science point of view. The hardest, we typically refer to natural sciences as the hard sciences and call social science as the soft science. But actually, the softest information is now coming from the hard science, and the hardest decisions have to be made by the soft sciences. So I would suggest not to have such meetings without proper social science people involved.
Yeah, thanks for this. Meanwhile, for the participants, if they have any question, please write their question in the
Vikrant, can I hear something?
message, and then we will read those questions. And with that, yeah, please,
I think we need to be more. I will add one point. Just we need to be more focus on process and methodology, so that beyond adaptation we can go to make the communities as resilient. So that's from my side.
Yeah. So so a bit more elaboration will help. So like how this method will lead towards the better adaptations. Professor Manish, you mentioned that a better methodology. So better methodology in terms of our understanding of the climate science, is it?
Yeah, our understanding of the climate science, and because you have a CMIP 5 models, you have a CMIP 6 models, all models result 8%, 8.1%, or 8.9%. So we need to be a little bit more investing in terms of money, in terms of hard works in these models to get more accuracy. And there are different methods. These methods, like mentioned, uncertainty. Some data uncertainty, some model uncertainty, some method uncertainty, uncertainty in the uncertainty. So all these problems couples. So that we need to be taken care of.
I think easier maybe to accept that CMIP 5 level models will never be good at regional scale. Temperature decorrelation scales are large, so they do temperature pretty well. Precipitation is like popcorn. You will not get from global models accuracy. That's why I showed the inhomogeneity of Indian rainfall. You can average over India and say it's only plus minus 10%, but for a farmer, that's useless. So instead of investing on CMIP 5 models, it's the idea of either statistical downscaling or regional Earth system models now show that with improved physics and ensemble physics, because before downscaling was just about improving orography. It's very clear that that doesn't work. You need region-specific convective schemes or fully resolved convections. You need land use change, which is very critical. Okay, Western Ghats vegetation acts as a capacitor. During active periods, it is taking moisture. During break periods, it is releasing moisture. Ganga Basin irrigation works as a capacitor for northeast regions for rainfall. So these kind will never ever be resolved in global models. So a different strategy of nesting will be required, I think.
Also, for this model, my questions to all panelist member will be: what about your overview, your viewpoint about the availability of the observed data set? Do we have the sufficient data, or there is a need to build up a good amount of observed data set, which will enhance the projection and then the forecasting capabilities of the models?
That's why I mentioned, sorry, I will go first anyway. Well,
yeah,
sorry, Vimal. Vulnerability is a big example. For example, to do that, you need socio-economic data. If you want to look at water quality impacts on health, for example, somebody from Indian Institute of Public Health, I was a co-author, worked on enteric fever from Surat and Ahmedabad. Remarkably different outcomes in response to El Nino and La Nina, even though they are so close. Such heterogeneity in rainfall, temperature is more uniform, but health outcomes, you cannot do this without having data. So people talk about water, energy, and food nexus, but actually it should be water, food, and health nexus. Energy is there, of course, but health is a huge loss to India in terms of morbidity and mortality. So I think data is a very serious problem. But the good news is that we shouldn't be sitting and having another panel meeting in 5 years and saying that data is a problem. Right now, what can we plan? How can we start identifying what data is needed to do resilience that Manish presented? What data is needed from the social science side? Vulnerability side is done using census data, which is only done once in 10 years, and you get taluka level granularity. How do you go beyond that? The last mile is always beyond that. But good news is that it shows vulnerability is reduced when you educate women to natural hydroclimatic hazards. So those kind of details are important for allocating resources to reduce vulnerability, increase resilience, and also to drive data needs. We don't even have a good sense of data needs right now. Sorry, go ahead.
Oh, thanks. Yeah, other panelist member would like to say a few points on this.
I think data. I would like to add something.
Yes, please.
Data observation, I think that's, I was working for Swansea River Basin, and I think we got only one gauge station out of 2 lakh some square kilometer of basin. So I don't know how, though we got the results we published, but there's always a sense of sincerity, authenticity, and of the data. So that's in some of the areas, especially there is a need to build up the data. Data is very scarce.
I think if I can add a
Yes,
comment
please.
here, I think maybe one of the outcomes of this pandemic might be that public health is elevated a lot, and that this type of data sharing publicly will become much more common. So I don't know about India, but I can check how many people in my postcode have COVID in this week. This type of high resolution health data for this pandemic in the UK is now publicly available. And you know, it was a huge effort to build up these platforms. But maybe, hopefully, as we come out of the pandemic, we can use some of these achievements also for much broader sharing of health data. I agree, you know, it's always the most tricky one to get your hands on, but it's also so important for a lot of the analysis we want to do.
Yeah, thanks.
I mean,
Yes, Vimal, please.
I can say data is always, I don't think we will reach in next 10 or 15 years when we can say we have everything what we need to understand the problem or to do the modeling or to understand, the factor that affects a particular problem like water, water, energy, food, public health nexus. So when we talk about public health, I mean, the problem in India is that we have all cause mortality data reported most of the times, and we don't have mortality, cause-based mortality data very well documented for most of the cities. And whenever heat waves occur, that data becomes very coarse, like DAAD or other sources, international organizations have put that data in public domain. But when you go to Ahmedabad Municipal Corporation and ask them that how many people died in different years because of heat wave, it would be very difficult to get the data. And same, like Raghu talked about the last mile problem, even if we use IMD forecast or any other forecast, farmers will complain like, you sort of predicted that it will rain tomorrow and or day after tomorrow, but it didn't happen in my village on my area. So I mean, these are the challenges that are going to remain, that how we can incorporate, because there are challenges at all across all the scale. When we come to country scale to regional scale, even regional models have known problems, and the Cardex effort was designed to help the adaptation, climate change adaptation in India or other countries. But that hasn't been, so successful, or that the credibility of even regional models were very well questioned, and not necessarily that when we apply regional models, we are going to get good results that can work at regional scale. So I think the lesson that we can learn is that how we can rely more on the observed events or the observational assessments that tells us credible that what has been happening and what is the impact. And we can then basically take some guiding information that if this happens, this was the impact and that's how people adopted. And that could be a sort of a line to sort of use observational in more sensible way to make the decisions even under the changing climate conditions. Because uncertainty scale, model scale, regional models still are working at 25, 10 kilometer, 15 kilometer grid size. And when we talk about the adaptation at local scale, village level or taluka level, that That is not sufficient. So there is no end that where we need to stop or where we can start. But the problem remains the same, that we have to make the decisions under uncertainty, what we know, what we don't know, and then we sort of decide that how we can move forward.
I think I should clarify a couple of things there. One, Codex is not a good example of downscaling. Monsoon is a very coupled problem. Indian Ocean is so warm and so close. So to take coupled model output from CMIP and then to downscale it with SST forced downscaling is just a very bad idea. So one that will not work. It will work for the US because it's very far from the ocean. For India, it will never work. So that's why I mentioned regional earth system, and I mentioned regional physics and regional vegetation, land use, etc. So there is earth system models implemented in China. It's getting very good results. The other thing is they don't work at 20 kilometers. Even NCMRWF is running at I think 3 kilometers or better for cities. So within, it depends on the time scale. Plus, I also mentioned statistical downscaling. So you have to decide on the time scales to get appropriate adaptation information. And the people's reliability, if farmers are complaining because in general, I would say IMD is not responding very well to customers. This is why SkyMet may be making some progress, saying, look, at least they seem friendlier than IMD maybe. But the demand keeps going up, and the probabilistic information has to be provided as well. You cannot say it will rain tomorrow. People have to get used to the idea that there is a 30% chance of rain tomorrow. And this happened in the US over 50, 60, 70 years,
Exactly.
right? So it takes time. So where we are now is a good place. So we have to identify what is working and how to grow it. So it's a matter of delivering usable information packaged properly for needs and sectors.
Thanks. And also about the scale, and then about adaptability and the decision making. And India is a large country and also very diverse. And we also know about the climate change projections are variable from basins to basin. Then how much that this decision making or the adaptability issues should be addressed more at the state level, where the state is going to take the decisions, because the challenges and then the issues will be different from place to place. I mean, some of the states are in the Himalayas, some of the states are in desert areas, some of the states are in the southern part, very close to ocean. And with those kind of variabilities, how much the role of decision making should be more addressed to states? I would like to have your viewpoint.
I think there are always governance issues that start. For example, CO2 is a global governance issue. It's well mixed, it's long lasting. So you have to deal with adaptation and mitigation of CO2 at global scales, Paris Agreement, whatever. But then sector wise, you have to go down. Rivers have catchment areas, multiple users, stakeholders, various requirements and data sharing or output sharing of forecasts of floods and droughts, etc. And if you want to do energy, then you have to go into local grid. And so there are multiple problems. Adaptation is not a one basket thing, right? So it depends on whether you are adapting to energy variability, like solar will be very good in Rajasthan maybe, and wind is very good in parts of Tamil Nadu and Karnataka, and I don't know, somewhere in the north as well, I'm sure. So I think you have to design a basket that is suitable in terms of the governance issues. Soil governance, for example, is a critical. Soil carbon is so ignored in India in terms of food security and health security and water security, right? So that will be much more of a local problem. So I think each problem will have a different scale, different need for information. But if they continue this S2S, the sub-seasonal to seasonal time scale, and develop ready, set, go framework for food, water, energy, and health, then they can begin to need the scales of those sectors by using a combination of downscaling statistically and dynamically.
Yeah, thanks. So we are approaching to time, but I have received one One question yeah, from Nirgant Harba. So the question is that which agricultural practice should be taken which leads to colossal crop loss in India, mainly caused by Indian monsoon shift due to land-ocean surface interaction? So, so I will repeat
I'm
the
a big
question.
fan of agroforestry. Sorry, I'm talking too much, Vimal, but I have been involved in agroforestry.
Please go ahead. I'm listening. You are most welcome. You know.
Actually, this question
So
was
you are
also
making
addressed to you.
very important remarks, and I
Yeah,
think
it is.
I'll ask my student to go through recording also, because these are some of the areas which we often find these are important, but we don't go into so much deep in terms of understanding the problem. So Raghu, you are most welcome. Please take your time. I'll listen you.
Anyway, we are
So
running
this
out of
question was addressed to you, in fact. So I first
to Vimal or?
Yeah, to you, Professor Raghu. Yeah.
Oh, okay. So thank you. So I've been working on agroforestry because it's a sustainable watershed management. It's a sustainable agriculture management, and it increases soil moisture persistence, drought resilience, groundwater recharge, reduces evaporative loss, provides post-monsoon income as well, reduces rural migrations to as migrant laborers and so on. And it also relates to other health problems because there are issues of farmers who go out as laborers often come back as alcoholics or bring AIDS back home and so on. So there are many social problems there as well. But the much more important thing is that the extremes are increasing. Soil erosion and runoff has to be managed. As they say, you make the running water walk and walking water stop. So agroforestry is also important because the pumping of moisture is coming from the Arabian Sea, which is very warming rapidly. And that supplies almost 30% of the moisture for the widespread extreme events that have become like 10,000 scale, 10,000 square kilometer size now. So we cannot control the ocean warming very easily. Only thing we can do is adapt land use and agricultural practices, right? So I mentioned changes in onset and withdrawal and distribution. So crop calendar has to be kind of looked at again. Farmers' mental model is to get prepared by April, May and expect June rain and then heavy rain, and then crop choices are wrong for the heavy rain or wrong time rain, rotting onions in the ground and so on. So the crop calendar has to be carefully looked at in terms of regional distributions of these extremes, etc. So it's a tough problem, but it is doable if we all put our heads together. But bring social scientists in. Bring social scientists.
Yes. And there's another question. It is extension to Professor Raghu as well. How can we improve monsoon prediction for a long period of time?
Yeah, I mean, there is, if you look carefully at the monsoon trend, like Roxy's paper, for example, it is pretty clear that there is still a 20 to 40 year time scale in it. And I mentioned that also in terms of the cyclones, because the cyclones that started hitting Mumbai in the last few years, it happened in the 1940s as well and around 1900s as well. So we have a very hard time separating the anthropogenic forcing versus natural variability in the monsoon at low frequencies. So the question then is, where is the low frequency coming from? Is it from high latitudes? Is it from the tropics? This has to be figured out. There is also a strong Southern Ocean connection, for example. So I think the prediction is going to be coming from predictability, which has to be understood by looking at the variability in the past records, which has, I would say, been done a little, but not a whole lot. But I think there is some predictability squeezable from existing data in terms of at least model experiments. So despite having dry terrestrial monsoon bias and so on, I think models can still produce decadal variability and decadal predictions because there is large-scale dynamics governing those, I think.
Raghu, may I ask one question with your kind permission?
Yeah.
So, I mean, see, we are low probably since last 1 decade or even more. I mean, you may have better idea. that these all CMIP5 or majority of CMIP5 models, or we can say probably with good confidence that 90% of CMIP5 models, and same for probably CMIP6, though there has been slight improvement in terms of large scale teleconnections and all, are not doing very well when it comes about the Indian summer monsoon, right? And this has been a known problem to climate modeling community. And so what do you think is the biggest challenge, that why we have not been able to uh, do improvements or kind of improvements when these models start working in better way as when it comes about the monsoon projections, or capturing some sense of the variability, observed variability in the Indian summer monsoon rainfall. So why it is so challenging? You please tell us that why it is so challenging to get the monsoon right in the climate models.
I mean, in my own opinion, we know very well that there is an intrinsic time scale of intra-seasonal active break distribution. Global warming, ocean warming, El Nino, NAO, everything is projecting onto active break periods. So the physics of active break is not very well understood. And if that contributes about 60% of the rain, then you are missing a lot of the explained variability. So the dry bias is coming basically because you are raining too much on the ocean and not enough on land. And we don't know whether that's because land processes, especially hydrologic processes like soil moisture feedback and vegetation feedback are missing, or is it because the ocean itself is wrong? So we are getting close to that, answering that, because the main thing to notice is that MJOs go eastward October to April, and then they begin to be steered northward during May to September. So we got monsoon intra-seasonal oscillation. So this fundamental physics of timescale selection of intra-seasonal in the tropics has to be understood. So MJOs have 5 theories, which is not good news because that means we don't understand it. And mesos have probably also many theories. So basically, more theories just means we don't know. So I would bet on monsoon intra-seasonal oscillations. And very specific processes are not being understood, now being understood in terms of the vorticity tilting and how that relates to convection, why the steering happens at all, and so on. So that fundamental time scale is really what is missing. Because monsoon, if you average and look at seasonal evolution, they will do great, but they do it without intra-seasonal oscillations. So obviously they are getting somehow the right answer for the wrong reason, but with a bias. So we have to understand that. But that's my personal bias.
No, I mean, what has been observed, like in these models, that they are too sensitive, overly sensitive to convective rainfall. So if you increase like half degree temperature or 1 degree temperature, your rainfall amount goes up like by 16% or 20%, or in some models even beyond that. So I mean, so I don't know what to say, because this is now India has its own Earth system model participating in CMIP6, and
Yes,
I
hope doing very well, by the way.
Yeah, I hope that this stands apart in terms of so this at least
it doesn't solve the convective level problems. The convective level problem is mainly because the data is very local and we are applying it as a global scale. And convection by definition is a popcorn. It's very local.
Yeah.
The measurements they made over the Western Pacific warm pool, they just don't work in the Bay of Bengal. So Bay of Bengal made its own observations under Jasmine and Bob Mex and Bubble and so on. So new understanding has to evolve. But in a model, in a global model, you cannot put different convective parameterizations everywhere.
Sure.
What you can do is ensemble physics, which is what regional Earth system models will give you. So in a region like the Indian Ocean, Codex is a waste of time. They should stop it for Indian monsoon, because it's a coupled problem and they shouldn't do uncoupled runs. Okay.
Yeah.
But regional Earth systems which are coupled and can do multiple physics in the model, can do ensemble physics, and actually good papers exist that show that they can produce tropical kind of elevated convection versus mid-latitude surface level convection by combining different parameterizations. So to the extent that we have to do parameterization because we don't know the fundamental physics of convection, we are stuck with those kind of solutions. But it's not hopeless. Let's try to think about models just to be a little philosophical. Given the top of the atmosphere forcing, they produce everything. It's like a car, it's pulling little to the right, so you fix it someday.
All right, thank you so much. Sorry, Vikrant,
Okay.
I sort of
no, it's
myself
excellent.
between you.
So we are now approaching towards time, and then once again I thanks all our panelist members, Professor Raghu, Professor Vimal, and Professor Manish for their insightful lectures and also thoughtful discussions. And now I will hand over this floor to Professor Manish Kumar to announce anything.
Yeah, thank you so much. I mean, I was sure that you will run it, and what this Trimurti and the purpose. This Zoom has placed you in the middle right now. If you will see, and rightly so, Professor Raghu. That and around you, the discussion went very well. Actually, this was amazing to learn about few things. And Vikrant Jain was giving the slowly the things, and we had a very nicely the session. I thought that maybe because we forgot the time. In fact, this is 9 p.m. and my students are going to have dinner. That's why. But thank you very much, Professor Jain, and all the panelists, and David. You have been here, and of course the Falguni, Kishore, and Alok. They are the one who are a kind of technical support, and of course all the participants who had must be immensely benefited from that. And once more that sorry for a very late minute invitation to all you people. Thank you very much for turning up.
Bye-bye. Thank you.
Thank you.
Thank you,
Bye.
Manish. Thank you, everybody. Have a great night.
Thank you.
Bye-bye.
Bye-bye. Good night.